Okay, so, you pulled out a picture of a surface that has exactly these characteristics, concave up in one direction, concave down in another, right? Except the surface you pulled up, if you look at it carefully, is like this surface would be, this saddle, rotated 45 degrees, so it's concave up in both the X and Y directions. Still concave down at 45 degrees, or concave, yeah, okay?
So that's why it's still not enough?
Yeah. So you gotta So we could be concave up in the both X and Y directions. But concave down in 45-degree directions, or in some direction that's not the X or the Y, right? I mean, it could be distorted. It might still be concave up in the 45-degree direction, but not in the 10-degree direction, okay? Well, you get that by looking at fxy, okay? So the test is this: at a critical point, we look at fxx times fyy, okay? Now, if fxx and fyy have opposite signs, you don't have a critical point, right? Okay? So this is positive if your concavity is the same, right? So I'll say that's positive if you have the same concavity in the X and Y directions, right? So we want to ultimately say that this is got to be greater than or equal to 0. It can't be negative. If it's negative, you know for sure that you have opposite concavities, right? Now we haven't talked about what happens if it's 0, and it turns out if it's 0, either thing could happen, okay? So we got to worry about that too, okay? But now to worry about what happens in directions that aren't the X or the Y directions, because weird things can happen if you go just a little ways from the direction of either axis, right? As is shown by the picture you have of a saddle turned at 45 degrees, right? Okay? So we've got to subtract fxy squared. Okay? So this makes the left-hand side negative. There's no relative max or min. I'm not going to go into any more detail about that, but if we have time we will do a proof of this, okay? First we gotta do proofs of the chain rules, and you gotta see that, okay? So maybe we'll do the proof of this, and maybe we won't. So your engineering heart might be happy just to have a formula you can use. Now, this is often called the discriminant, and we use capital D. Okay? So let's look at an example. And what are we going to use for the example?
2 square root of xy.
Yep. Now, I think the one you were looking at is square root of x squared minus y squared. Okay? And of course, x squared minus y squared is an upward parabola in the x direction, right? And a downward parabola in the y direction. But I don't think it was x squared minus y squared. I think there was an xy term in there too. Either that or I was looking at the picture wrong. Anyhow, it doesn't matter. We'll look at that one also. Okay? So, we want to consider this. So, go ahead and apply the test. Now, yeah, first of all, find your critical points. Where are your x and y derivatives 0? Is there a point where they're both 0? And that's relatively straightforward, okay?